If you are listening to this, chances are either you or someone close to you will suffer a stroke. There's 800,000 stroke cases each year in the United States, making it among the top 5 causes of death. However, most strokes are actually not fatal, instead causing debilitating side effects, anything from memory loss to blindness. This is because strokes cause an area of brain damage called a lesion, which is visible in MRI scans like this one. One stroke symptom I will mention is called stroke-induced cardiomyopathy. This is when a stroke interferes with areas of the brain responsible for cardiac function, resulting in complications and even heart failure. Early identification of stroke side effects is critical in treating and saving lives. However, diagnosing neurological conditions is complex, as many of these conditions are subtle, misattributed to other causes, or, as is the case with cardiomyopathy, may be impossible to notice until it is too late. Meet LesionInsight, a machine learning-powered solution to the problem of stroke symptom identification for use by doctors and hospitals. Let's see this product in action. So first, go to our webpage, lesionbank.org. From here, click on Predict, and you can either upload your patient's imaging data or draw the area of lesion directly onto a brain template. Click Generate, and it will make something called a lesion network map, which is used as the input to our predictive model. The results are summarized in a table, rank ordering the most likely symptoms. For this particular lesion, the most likely symptom was memory impairment, which makes sense as this lesion was in the hippocampus, the brain's memory center. The brain is made up of 100 billion neurons interconnected through synapses. And for this reason, a brain lesion actually disrupts an entire network of brain regions that extend beyond the lesion itself. This lesion network map is invisible to regular MRI and can only be discovered through intensive processing. This lesion network mapping processing has never been clinically implemented for a variety of limiting factors. For one, it requires a lot of coding knowledge, as well as access to data sets that are closed source or simply don't exist. But most importantly, it requires a lot of computational resources. For generating even one lesion network map using traditional methods, it can take many hours to even days of continuous processing. LesionInsight overcomes these challenges, making lesion network mapping a viable tool for clinical diagnostics for the first time ever. We cut down the processing speed more than 1,000-fold via a completely novel technique that we've called the pre-computed connectome. This is essentially a highly optimized data library that enables us to create these lesion network maps in about 60 seconds. We also created our own custom tool that allows for outlining brain lesions within the browser and assembled the world's largest open-source lesion dataset of its type, including more than 100 different symptoms, including rare ones like cardiomyopathy. I also wanted to mention some key engineering details. We scraped PubMed using large language models and convolutional neural networks for image analysis and created a large cohort of data for training. We trained a predictive model using a technique known as principal component analysis, followed by multinomial logistic regression. And this predictive model achieved more than 70% cross-validation accuracy at recognizing symptoms just from MRI scans. We deployed this technology in a web application utilizing a Django backend, a Postgres database, and AWS for cloud infrastructure. I also wanted to mention the developmental journey. We started about a year ago, and since then we've pushed more than 400 prototypes to our GitHub repository, and we presented this technology to Harvard Medical School, with which we made a valuable partnership and were able to interact directly with clinicians and even researchers. LesionInsight isn't just for strokes. There are many brain diseases that can actually cause areas of brain damage called lesions, including multiple sclerosis, Alzheimer's disease, even brain cancer. This tool can inform neurosurgeons in advance of the possible side effects of surgical resection. LesionInsight isn't just an idea. It's already built, and it already works. Thank you for listening.
Thank you. Well done. So this is different from the game Star Wars Legion, right?
Yes.
Okay, you have 5 minutes with the judges.
So first of all, my twin brother, who helped me build this, is going to join me for the Q&A.
How do you verify the analysis is correct? Like you've done all this analysis, you're doing all this machine learning. How do you verify that analysis is correct?
So that's a great question, and I'd love to clarify. So we have a big cohort of lesions, about 1,000 lesions mapped to different symptoms, and we build this predictive model using a leave one out approach. So we leave out one particular lesion and rebuild the whole model from scratch just to predict that one lesion that it's never seen. That means that the model doesn't overfit, and it's able to predict for lesions that it's never seen. And we iteratively did this leave one out cross-validation, and across all different rounds of cross-validation, the overall net accuracy was about 71%. Does that answer your question?
Yeah.
Is that satisfactory, 71%, just dealing with patient expectations for experiencing certain symptoms? Does that meet the standard of care that's expected?
That's also a good question that I'd love to clarify. So first thing to know is that our model is actually getting more and more accurate. When we first trained it on a smaller lesion cohort, we were in the 50 to 60% accuracy, and as we expanded to include more and more lesions, our accuracy increased. So as this thing gets more and more used, we're actually going to have access to more data that's going to increase the accuracy. Another factor to consider is currently our model doesn't know any demographic information about the patients, only the anatomical structure of the lesion. Once we incorporate demographic information like age, sex, or even BMI, you're going to see a lot more increases in accuracy. Not only that, but this isn't necessarily going to replace regular diagnostic procedures. It's about rapid screening of anatomical scans to give immediate feedback. So there's certain symptoms that doctors are never even going to consider, but by passing this through a model that instantaneously identifies the likely symptoms, they can then proceed to have more robust diagnostic procedures. The advantage of this is obviously regular cognitive examinations like the Montreal Clinical Assessment actually require a follow-up appointment with a specialist, and even the test itself, the gold standard is the Montreal Clinical Assessment, can cost more than $100. So there's definitely certain advantages to have this automated screening of patient imaging data.
What's your target if it's 71% currently?
Sorry, may I just add to that answer? So our model also will give a probability that its diagnosis is correct. So although it's 71% accurate on average, if it's extremely confident for one specific case, it'll tell you like 98% accurate. Or if it's not confident, it'll tell you, say, 30% accurate. So it's not going to be a uniform accuracy for all cases, and the doctors will be able to tell when the diagnosis is almost 100% accurate.
Yeah. And to answer your question, how accurate do we think this can get? I am optimistic that we can get well over 90% accuracy when we build the data set larger and we incorporate other variables from the actual patient demographic information.
Who will be the primary customer for it?
Can you repeat that? I couldn't quite hear.
Who will be your primary customer?
So I foresee this technology being used by hospitals and clinics. So it would be directly integrated into the hospital infrastructure to automatically screen patient imaging data. It can also be used by any doctor that has some amount of neuroanatomical experience just to automatically screen if you have access to patient imaging data, CT or MRI. So definitely the target audience is hospitals and clinics, and then maybe more specific uses by actual clinicians themselves.
In addition, like neurosurgeons who are planning which direction to cut into a brain can use this tool to find the best place to cut in with the minimum brain damage.
Guys, this is exciting technology. It's a great, looks like a great product. This isn't unique to what you're working on. I mean, this is being done, a lot of research is going on in this area at other institutions, National Institute of Health, et cetera. What is unique about the way you're approaching it?
Yeah, so that's a good question. So as someone who's really involved in this area of research, we're doing something that's completely novel, which is we're using functional connectivity information in order to identify the global patterns of disruption throughout the brain. So there's a lot of labs that are using convolutional neural networks to try to diagnose radiological scans, and they're achieving fairly good accuracy, but they're only basing that off of the anatomy visible within the scan. Whereas our pre-computed connectome enables you to identify the global connections that are disrupted by the brain lesion, which is really not something that anyone else is doing. And being able to use functional network mapping in such a responsive time frame is really never been done before.
Well done. Thanks, guys. Well done. Awesome. Thank you so much.